Okay, let's get started. So, today we're going to be talking about arc length, which is section 8.1. And what is this about? So, we're going to learn how to calculate the length of a piece of a graph above whatever interval we want. Suppose we have interval a to b, and we want to know what is the one-dimensional length of the graph above this particular curve. So the length of this thing I'm outlining in red here. Okay, I'm gonna show you a formula for this. I'm gonna explain why it's true, and then we're gonna practice calculating it. So let's think about the simplest cases where we actually know something about this. So if we just have a constant function like this, just let's call it L, just with constant value L, and we ask ourselves what is the length of the graph of this constant function above a to b, then that's easy, right? So this length is just going to be b minus a. Sorry, right? That's clear. Yeah. If we have something just a little bit more subtle, something like this. Suppose it's a function with some kind of a slope. Okay, a slope like this. Yeah. Suppose this function is given by ax plus b. Yeah. Let's think about what the length of the graph above this is. Well, let's see. If we draw a line like this, yeah, then the length that we're actually interested in is this thing right here. And what we see is that we've drawn a right angle triangle. Yeah? Where this side over here, this side has got length b minus a. Yeah? So if we knew what this side here was, then we'd be able to figure out this length just by Pythagoras. Yeah? So looking at this picture, knowing that this is the graph of the function ax plus b, tell me about what you think this length over here is. Come on. Look at the picture. This is our graph. What is this length? Yes, if we let f be this thing. Yes, it will. Let me actually change, because we already used a and b. Let's call this c, and let's call this d. No? So this is a linear function, and its slope is given by c, right? Yeah. So for every whatever x we go along, we go up by c times x. That's the meaning of the slope, right? Yeah. So here we're going along by b minus a, and therefore we have to go up by c times b minus a. Yeah. We know this stuff, right? We talked a lot about affine functions, about tangent lines, about slopes. This is all Calc 1. Yeah. So this for sure is going to be c times b minus a. Yeah. This is a kind of key point. So the whole thing will make sense if you're happy with this, and it won't if you don't. So give me a thumbs up if that makes sense to you, and do this gesture if it doesn't. Okay, so therefore by Pythagoras, what's this distance over here? It's this thing squared plus this thing squared square rooted. Yeah? Yeah? And if we do that calculation, what's that going to be? So b minus a squared plus c times b minus a squared square rooted. We can pull out the b minus a. We're just going to have b minus a square root of 1 plus c squared. Yeah? That's what we have. Cool. So in this very simple case, where we have just an affine function, or I should say a linear function, we call them linear in calculus, we can figure out what the length of the graph above A to B actually is. And it's pretty easy. It's just Pythagoras theorem. Yeah? And what we're going to do is we're going to have a formula for any function, and it's actually going to come down to this picture. It'll come down to this. So if you understand this, the formula is going to make sense. And if you don't, then it's just going to be mysterious. Now, I'm going to explain this formula. I am not going to prove it. This is not a proof. It's going to be an explanation in terms of pictures. And that's something I'm going to do going forward for all these formulas that we'll encounter in this part of the course. So we're going to do a little bit of introduction to the multivariable calculus in the next sections, 8.1, 8.2. Then we'll talk about sequences and series, and then we'll go back doing some more multivariable calculus right at the end. If you do multivariable calculus, and I hope you all do, the course is full of formulas to describe various quantities, like, for example, this, the length of a graph above A to B. And all of these formulas fall out very naturally, very simply, if you have the pictures. And I'm going to show you how. If you don't, then they're just completely mysterious. They're just like a pin code. You have no idea why they're true. You will not be tested as to why this is true, but it is super important that you understand something about why it's true. So back before the pandemic, I would try and sell this by saying, if you just try and memorize formulae, go into exam, you can get it wrong. Now that we have the pandemic and the chaos that's consequence of it, and we have cheat sheets, then I can't sell you that reason anymore. So I will tell you the real reason I care so much about this. And that's because, as I said, this is a language whose meaning is more important than simply being able to apply a sequence of algorithms that will teach you. And if you understand the meaning of the language, then the things we express in the language make sense. And that's valuable knowledge as you go forward in your studies, doing more and more mathematics. It will be a meaningful thing. All the subjects which you study that are written in the language of mathematics will make sense to you if the meaning is making sense to you. So while you will not be tested on what I'm about to explain, if you are serious about your studies, certainly if you plan to go ahead and study at a higher level at any graduate topic of any kind in the sciences or engineering, then you want to develop this level of understanding. Then you want to do this. You do not want to take away from this course simply a bunch of algorithms that you can use to solve particular kinds of questions. You want to understand the meaning of this language. So please do not fade out or switch off or not pay attention. Unless you are absolutely sure the only engagement you want with maths for the rest of your life is just to pass the absolute requirements for your degree and then never touch it again. If you're sure that that's what you want to do, then sure enough, don't pay any attention. It's not, you won't be tested on what I'm about to explain. If that's not you, then please pay attention. This is more important than learning to integrate by parts. It's more important than trig substitution. It's more important than most of what we've been talking about for the last 3 weeks by a factor of 10 or maybe a factor of 100. So pay attention to the explanation. The algorithms are not the thing I really care that you understand and can do well, even though that's what we're testing you on. All right, let's get into it. So we believe this formula if we have an affine function. Yeah? We believe this formula if we have an affine function. What if we just have an arbitrary function? Well, this is a strategy that we will use all the time in trying to understand things. It's one of the basic principles of calculus. It's something which in my Calc 1 course, students from then already saw. We understand things by cutting things up into little pieces, because on little pieces, they are easy to understand because they are differentiable. They look like affine functions. That's one of the key ideas of calculus. That if you look on a very small scale, then we have something that's very easy to understand because it looks an awful lot like its tangent line. Yeah? And what is this? This is nothing but a tangent line, right? This affine function could be the tangent line of a function at a particular point. right? So we can understand things when they're affine. And on a very small scale, they look like they're affine. When I say affine, I mean linear. So in future maths, you'll learn that this is not linear, it's actually affine. In calculus, for historical reasons, we call it linear. So if you wonder what I mean by affine, I mean linear. So for this course, affine and linear are the same words. So we understand when things are linear, you know? And things are linear on a very small scale because by differentiability. So that's how we're going to understand it. We're going to cut them into very, very small scales. And then we're going to understand a little tiny piece using the fact it's very close to just being a linear function. And then we're going to put the pieces all together. And then we're going to pass the limit. Okay, let's see how this goes. So suppose we have differentiable function f from a to b, differentiable. And we want to understand its arc length. Let's draw a picture. Suppose it does something like this. Okay. So what we're going to do is we are going to cut up the interval a to b into little pieces, equal sized pieces, right? As we've become very used to doing from Riemann sums, from integration, right? So we're going to let delta of x be b minus a over n for some large number n, which we'll choose later. Yeah, and then we're going to let x0 be equal to a. Yeah, and then we're going to define all these little pieces going across, cutting up this interval a to b into equal sizes, right? So this is our first guy, x0. We're going to find xi plus 1 to be equal to xi plus delta of x. And we're going to do that for I is equal to 0, 1, all the way up to n minus 1. Yeah? You all saw this before. This was just how we learned about calculating Riemann sums, right? So this guy is xn, right? And x1 is what happens when we move delta of x along, right? So x1 is here, x2 is here, and so on and so on. Yeah? Yeah, the stuff is what you learned already. So each one of these intervals is exactly delta of x long. Yeah? And they cut up the entire thing. Yeah? So we're going to just pick some arbitrary interval. Let's say xk to xk plus 1. Yeah? And we're going to look what's happening above here. Now, since our function is differentiable, we can take the tangent line at the point xk. And the little piece of the graph above the interval xk to xk plus 1 is really a lot like just the length of the tangent line, because the tangent line is very, very close to it. So let me write in words what we're doing. So we cut a to b into intervals, let's say equal size intervals. xi to xi plus 1, where I goes from 0, 1, all the way up to n minus 1. Okay, that's our n equal size intervals. We're cutting them up. So pick an arbitrary interval. So pick one. Let's say it is xk to xk plus 1. Yeah? And then look above this interval xk to xk plus 1. And what we see is that this thing is an awful lot like its tangent line. So I'm going to take this circle here, and I'm going to blow up everything in this circle into a bigger picture. Okay, I'm going to do it here. So imagine you have a microscope blowing up the picture here onto this size screen. So what do we have? This here, say, is our function xk. Sorry, as our function f. Here is where we take the tangent line. And the tangent line kind of looks like this. Okay. This is above xk, and let's make it consistent with our picture. And then this is above xk plus 1, but xk plus 1 is just moving along from xk by delta. Okay? Yeah? Everybody with me so far? Just drawing pictures, yeah? We're just drawing pictures, stuff that we know. All right, so if we want to find out this length here, which I'm outlining, of the graph above this interval, we can make a very good approximation to this length by just figuring out the length of the actual tangent line, because it's really, really close, right? In fact, the smaller delta is, the closer it is. Differentiability exactly says that if we look on an interval of size delta of x like this, the error between the tangent line and the function is way, way, way smaller than delta of x. So this gap here, even though I've drawn it fairly big to have a picture to give you, is tiny, tiny, tiny compared to delta of x. Okay, that's what differentiability means. Yeah? That's exactly the definition of differentiability. Yeah? So if we want to approximate, and outline it again, this graph here, a very good approximation is just to take the length of this thing here, the tangent line we've taken at that point. Yeah? So let's draw the information we have. So this is delta of x, right? What is this slope here? What is this slope? Sorry again. What is the slope of the tangent line at this point, xk? What's the slope of the tangent line? It's just the derivative of f at the point xk, right? Recall the tangent line to f at some point, let's call it a f of a. Let's just call it just a, just define it from the x-axis, is given by t of x is f prime of a, x minus a plus f of a. Because the tangent line is just the linear function that goes through this value a f of a with this same slope as the function, right? And the slope of the function at the point is just the derivative. Yeah? This is stuff you learned in Calc 1. This should be solid for you. And if it's not, you've got to go back and make sure you're happy with this. This is absolutely key fundamental concept in calculus. The reason calculus works is that we get away with dealing with a simple thing like the tangent line rather than the actual thing because of differentiability. Okay? So if that's not clear to you, go back, talk with me after this class, we'll recap it. But that is stuff you have to know. Okay? So this red line I've drawn here is the tangent line. And its slope is given by just the derivative of the function at this point, xk. So, what do we know? We know the slope is f prime of x, f prime of f at xk. Yeah? So by exactly this reason over here, this distance is f prime of xk times delta of x. Exactly the same reasoning. Yeah? Give me a thumbs up if you're with me. Cool. All right. So exactly the same reasoning again tells us that this length here, the length of the tangent line, is given by delta of x square root of 1 plus f prime of xk squared. Yeah? Cool. And this is not quite true because, there's a little bit of an error, right? But the size of the error is way, way smaller than delta of x. It's way, way smaller than delta of x. Yeah? So we're going to write this. So length of f above xk to xk plus 1 is very much like just this quantity, delta of x 1 plus f prime of x k squared. Yeah? All we've done is draw pictures, and now we're describing what we see in the language of maths. That's all we're doing. Yeah? Cool. And the error is some tiny, tiny fraction of delta of x. So this thing is small, it scales down like delta of x, and there's a tiny, tiny error which is way, way smaller than delta of x, so we're just going to forget about it. So we put this approximate sign to say that this is very close to the actual answer, and there's like a 1% or a 2% error, right? In fact, the smaller delta gets, it goes down from 1 or 2% to 0.1 or 0.2%. Yeah? In fact, the error goes down to negligibility as we let delta of x goes down to 0. Again, just because this gap is way, way smaller than this gap. Yeah? Cool. So we know the length of the curve above one of the intervals. And now if we just add up all of the little pieces here, if we add up the length above this interval and the length above this interval and the length above this interval and the length above this one, that'll give us the entire length. Yeah. If we cut up a piece of string into n equal pieces and we measure the length of each piece and we add them up, that's the length of the piece of the string. Yeah. Cool. So the total length of curve or graph is the sum, and we have n of them. We start from I equals 0 to n minus 1, each one of these expressions. Delta of x like this. Yeah? And then there's a tiny, tiny error, but we're forgetting about it because it's not important compared to the size of everything else. Okay, look at this expression here. Yeah? This is an approximate answer with a tiny, tiny error. The error gets smaller as delta goes down to 0. We want to get an exact answer, so we're going to let delta go down to 0. Yeah? And let delta go down to 0. We're going to pass to the limit, the other tool we have from calculus, or one of the other main tools we have from calculus. All right, so look at this expression. Tell me where you've seen expressions like this before. What kind of thing is this? What object is this? What do we call something like this? A Riemann sum, right? And as we let delta go down to 0, it's going to pass to an integral. It's going to tend to the limit to an integral, right? All right, so tell me what integral this tends to as delta goes down to 0. This goes to what? Yes, but what's the formula for the length of the line? What can we deduce from this expression? Let's do a little look at Riemann sums, right? So what you learn about Riemann sums is about finding the error underneath the graph, right? And then we just cut things up into rectangles, right? Where the base was delta of x and the height was g of xi. If this is the function g, yeah? So I know this is small, I'm running out of space. So if we had an expression like this, I equals 0 to n, g of xi, delta of x, yeah? What hopefully all of you would recognize is that each one of these expressions is just the area of one of the rectangles, yeah? Because g of xi is the height and delta of x is the base. So we add together all these rectangles, and that's going to give us the area underneath the graph, so it's going to tend to the integral from a to b g of x. Again, if you turn this into pictures, then this is meaningful. This is clear. Yeah? This is natural. Yeah? And that's what I'm hoping you should be at the position of doing. You should look at this expression and in your head see a bunch of rectangles underneath the graph of a function. And then you can just see that as the base of the rectangle gets smaller and smaller, then that thing approximates the area underneath the graph. That is what I mean by this is a language that describes pictures in your head. This is describing this picture, and you can see that this thing approximates the area underneath the graph as delta goes down to 0. Yeah? That's when this stuff becomes meaningful for you. Not when you remember something, but when you see it. Okay? Cool. So that's for a general function g. Yeah? Now look at this again. Tell me what the Perfect. Thank you very much. That's wonderful. Okay. Is everybody happy from this to this? Cool. All right. Now that we have the formula, we can just calculate. We can just calculate. This thing that was somewhat difficult to understand, we can now just calculate. We can find out the length of the graph above any interval by something like this. Yeah, we can find out the exact answer. And that's really strong. That's really powerful. That's the yin and yang of calculus. There are the two main ideas in play. The first idea is that differentiability means that on a very small scale, a function is very simple because it's like its tangent line. And the second idea is that we can add up tiny, tiny, tiny quantities via this new form of addition, this generalized addition, which is integration. Yeah? These ideas perfectly sync with each other to allow us to express things like this that otherwise we couldn't. That's how calculus was invented. That's what it was invented for. If you think about calculus 1, you learned about the volume, right? The volume of some object. And we learned about it by slicing things into little tiny slices. Yeah? Thinking about what is the infinitesimal area of each tiny, tiny slice, infinitesimal volume of each tiny, tiny slice, yeah? Yeah, which was just the area of the cross-section, yeah? And then integrating it up. Yeah? And the way you learned that was just considering cutting this up into a little tiny thin slice and then adding up the thin slices. Yeah? And then we passed to the limit. That's exactly the same procedure. Yeah? So every single formula in calculus works this way. You look at a tiny, tiny scale, you understand things on a tiny, tiny scale, yeah? And you let the scale go down to 0, yeah? And then you go from a sum to an integral. So if you didn't see the volume formula explained this way, go and look on my videos from Calc 1. I explain the volume formula in exactly this way. And I explain all the other formulas, the volume via doing shells in exactly this way. Every single formula follows in exactly this way. It's what I call the Riemann Sum machine, because the same strategy, the same thought process gives you all the formula. And if you're comfortable with it, then all these formulas make sense. They're natural. This thing is just this thing. It just follows from Pythagoras' theorem. Huh? This is not a mysterious thing now. At least it shouldn't be. Huh? And maybe this is too fast for you. But if you watch this again, this will make sense. This will make whatever amount of sense it made before, it will make whatever, 40% more sense. And maybe 100% more sense. Maybe it'll completely make sense to you. Huh? But this is what I want you to do. I want you to understand why this stuff is true. This is not a proof. It's an explanation. It's an explanation why we have this structure. Okay? Huh? And we can believe it now. We can believe this formula is meaningful. We can have an idea why it's true. And now we can just use it. And this whole section, what you'll be examined on is using it. And using it is just doing an integration. So, example 1. Find the arc length of y squared is equal to x to the 3 between 1, 1 and 4, 8. Okay. There we go. There's our function. Okay, so this guy has got a couple of solutions when we take the square root. We have the plus and minus part of this graph. But since it's saying just between 1, 1 and 4, 8, then that means we're going to be considering this function, y of x is equal to just x to the 3 over 2. Because if we just put y of 1 inside this, we get 1, so it starts at 1, 1, right? And if we put y of 4 into this, then the square root of 4 is 2, and 2 to the 3 is 8. So this is the part. This is the half of this function that, or the half of this equation. This is the side of, I find it difficult to express this. Let me try that again. So when we try and solve something like this, y squared is equal to x to the 3, then we have two potential solutions, right? Like this, yeah, plus or minus, yeah? And each one of these will give a different curve, yeah? And all the points on the curve given by the plus will satisfy this, and all the points given on the minus will satisfy this. Yeah, see what I mean? Give me a thumbs up if you're with me. Cool. But since it's asking us between 1, 1 and 4, 8, so this is 1, 1 over here, and 4, 8 is, say, up here, then we know it's the part of the curve for the positive, not the negative. The negative is the mirror image across the x-axis. Yeah? Everybody with me? Cool. All right, so this is the thing we need to calculate. This thing, the length of this thing, yeah? From here to here. So we're integrating from 1 to 4. Yeah? Now that we know that's true, we just apply the formula. So this is our guy. So y prime of x is 3 over 2 x to the 1 over 2. Yeah? And then our formula is the integral between 1 and 4 of the square root of 1 plus y prime of x squared dx. Yeah? Yeah? And then we just put that in. So everybody who's here, please type in here in the chat box so I see how many people are with us. Okay, let's just do this calculation. So this thing is this guy, right? So when we square it, we're going to have 9 over 4 x dx, like this. Yeah? And then we're going to do a sub, so we're going to let u be 1 plus 9 over 4 x, therefore du equals 9 over 4 dx, therefore dx is equal to 4 over 9 du, like this. And then this guy, I'm going to change the limits. So when x is equal to 1, then this thing is going to be 1 plus 9 over 4. So that's going to be like 13 over 4. That's 13 over 4. Is that right? Yeah. And the upper limit is when we have x equals 4, and then this just becomes just 10, right? And then this is the square root of u. This dx has become, let's put this 4 over 9 over here. And now it's just this, right? So it's now pretty straightforward integral. So then it's 4 over 9. Well, it's pretty straightforward even from here. And then 10, 13 over 4. And then what's the antiderivative of this? We're going to take u to the 3 over 2 times 2 over 3. Yeah, if we differentiate that, we get this. Huh? And then we try and clean things up. So we can have 2 times 4, so 8 over 3 times 27, right? And then we're going to have 10 to the 3 over 2 minus 13 over 4 to the 3 over 2. And that is our answer. Everybody happy? Yeah, so the actual calculation of the integral was easy. And that is what you're going to have to practice. It's simply using this formula. So you're going to be given something like this, and then you'll have to understand what the question is asking. It's asking for the answer, and simply apply the formula. If the explanation makes sense to you, if you are solid on it, then this is natural. You won't get the formula wrong, and you'll just do this really easily, really quickly. Okay, cool. So let's talk about another concept, which is in this section, which is the Arclength function. Okay, it's decently well spelled, I guess. So let's look at this. How we fit in? Okay. So if we have a function like this from a to b, and we want to know the arc length from the initial point A up to some point x, okay, like this, then that thing will increase as x increases, right? If you're happy with how we got the original formula, then the following should make sense to you. Let's follow notation of the book. Calls it S. We write S of x. Let's think what it's going to be. It's the arc length between A and x, right? So we're going to have the same formula as before, right? With the endpoints A and x. But since x is now used as the endpoint, we can't integrate in x. We're going to use a different variable. We're going to call it t, right? So we start with A, we end up with x, and then it's just the formula that we know before, right? So it's 1 plus f prime of t squared. Yeah, this is the formula we know before. This is the Pythagoras structure that we know. Yeah? And then that thing is our arc length formula. Or arc length function formula. Yeah? If you're happy with the previous explanation, then this should be meaningful to you. Simply because this is the picture. This is the thing that we're trying to come up with, right? Exactly the length of the graph between A and X. Yeah? Yeah? And just applying what we know, that is just integrating this expression between A and X, and that's what we've written here. So what we've done here is we've described in the language of maths what this thing has to be, just the length of this thing. You feel okay with this? Yeah? Cool. And that's all this thing is. So we are going to calculate some arc length functions. Here's example 4. We'll start it off. We'll have to erase the board to finish it. Example 4. Find the arc length function of this guy. Y of x is equal to x squared minus log of x over 8. Starting from the point P1, 1. And let's just check if we put 1 inside this thing, y of 1 is 1 squared minus log of 1 is 0. So indeed it starts at 1, 1. Yeah? Cool. So that's our problem. Let's y of x is x squared minus log of x over 8. And we wanted to find the arc length formula starting from 1, 1. Perfectionistic. All right, so we know the formula, we're just going to calculate it, right? Let's put down the formula. So s of x is equal to the integral from 1 up to x of square root of 1 plus f prime of x squared dx. Okay? And then we just, in this case it's y. And then we just calculate what y prime is. We put it in the formula. We calculate this integral. It's not x, it's s. Because we picked x already. So, y prime of t squared dt. Okay, so what is y prime? So I've written it in x like this. Now we're integrating with respect to t, so we're going to write it in variable t and take the derivative. It's exactly the same, right? If we add this step, then it's just t squared minus log of t over 8. It's no problem, right? And then we just differentiate. We're going to have 2t, and we differentiate log. We're going to have just 1 over 8 times t. Yeah? Cool. And then we just put it in the formula, right? So if we consider 1 plus y prime of t squared, it is 1 plus this stuff, 2t minus 1 over 8t squared, which is equal to 1 plus 4t squared. We're going to square this guy. It's going to be 1 over 64t squared. And then this times this, and there's 2 of them. We're going to have minus a half, like this. Yeah? And then that's this thing squared. This thing over here is this thing squared, and that's our original 1. Yeah? Everybody with me? Cool. All right, so it's now 5 past, so those of you who need to leave. I'm going to keep talking and maybe do another example after this for those of you still interested. It's all going to go on YouTube later for you to watch in its completion. All right, let's look at this. So we have 1 minus a half, so it's going to have 1 over 2 plus 4t squared plus 1 over 64 t squared, like this. Yeah? And these integrals have to have a way to actually calculate them, right? And square roots are a pain, right? So what we're going to try and do is take the square root of this expression, yeah? And there has to be a way to do it, right? So previously, inside the square root was a nice linear term, right? And then it was just a u sub. That was easy. This thing obviously is not a linear term, right? In fact, for calculating square roots, our options are pretty limited. This is also not going to be a trig sub. It's not any kind of a plus minus a squared plus minus x squared expression, right? So there has to be a way to make sense of taking the square root of this. Yeah? Yeah? And what you will hopefully guess is that given that when we squared out this expression, we got this thing, we end up with something very similar here, yeah? Except the minus a half goes to plus a half. Yeah? And if you are noticing that, you might think, okay, but if I had just 2t plus 1 over 8 times t, then I square it out. I would still get this thing, I'd still get this thing, but now I wouldn't have a minus a half, I'd have a plus a half. Yeah? And if you notice that, then you would be set, because you would see that, okay, then this is just 2t plus 1 over 8t, everything squared. Yeah? So I told you there are just a fairly limited number of forms we can actually give you where you can calculate the integral. This is one of the forms. So if you end up with something kind of complicated looking that you're trying to take the square root of, there has to be a way to write it as a square. And the clue again is the fact that we squared this thing to get this expression in the brackets, and this expression is very similar. Yeah? And we notice that if instead of having a minus, we have a plus, then this thing squared is unaffected, the second term squared is unaffected, but the mixed term is affected, and that goes from being minus to plus when we have a plus. Yeah? Do you see what I mean? Yeah? So if you're trying to square root some complicated looking expression from doing these kind of integrals, just look carefully and you'll find there's a way to square it, to write it as a square of something. Yeah? So, square root of 1 plus y prime of t squared is just the square root of this thing, which is just 2t plus 1 over 8t, like this. Yeah? Good. And then it's easy, right? Then it's just an integral. So this thing, using our formula up there, is an integral from 1 to x of 2t plus 1 over 8t dt. This is an integral we can do. So it's from 1 to x. The antiderivative of 2t is just going to be t squared. The antiderivative of this thing is 1 over 8 log of absolute value of t. T is positive, so we just write like this. Yeah. Then we just put the numbers in. So we're going to have x squared minus 1 plus 1 over 8. And then log of 1 is 0, so it's just log of x. Yeah. So this function is the Arclength function, right? So we know that our curve is this guy. It is y of x is equal to x to the 3 over 2, yeah, from 1, 1 onwards, yeah? And for every x, we have that this length here that we're drawing. I don't know if that looks very different for you. Let's make the color, okay, whatever. Let's make the color blue as well. This thing here, yeah, is given by this expression, right? It obviously increases as x increases. Yeah? If it doesn't increase as x increases, then something's wrong. Yeah? Cool. So the actual calculation, once you know the formula, is just using the stuff that we already know how to calculate. Yeah? Cool. All right. Yeah, let's maybe wrap it up with just this example. So tomorrow, Laura's going to do many more examples of doing these kind of calculations for you. Yeah, this should be a straightforward subject to get points on. It's simply knowing the formula and getting the integration right. So you already learned about integration. So as you have your cheat sheet. So obviously take advantage of that, like everyone else is doing. But if you're in the exam and you have faced a question like this, and the only way it makes sense to you is to look back at your cheat sheet and then write down this formula, then that's not the position you should be in. That's not what I'm aiming for you. I want you to be in the position where if you're asked a question about the arc length of a graph, then this picture comes to mind for you, that if we just have a nice affine function, cx plus b, then we know that the length of this thing, if this is a to b, just by Pythagoras, is going to be just b minus a square root of 1 plus c squared. I want this picture to come to mind for you. And then from this picture, I claim that the actual formula, that integral from a to b, the square root of 1 plus f prime of x squared dx for the length above a to b, this too should be natural. If you're happy with this, you should be happy with this. And then that's what I want you to do. Ideally, you won't need to look at this. I promise you can be in that position. You will be able to do that. Just look over the explanation, play it over, and then try and figure it out for yourself. Take a blank sheet of paper and ask yourself, what would be the formula for the arc length? Well, I know this special case, I know the strategy, and then recover this for yourself with the explanation I gave. And if you do that just a couple of times, it'll be in your head for the rest of your life, and then all these other formulas will also make sense to you. that is what I ideally want from all of you. So if you're serious about this, that's what you'll try and do. Okay, so that's it for today. I have office hour now. Stick around if you have any other questions, and otherwise I will see you all on Wednesday. Have a great day.